Good morning, here we are at the physics video lecture. Once again, physics 2A, video lecture 29. So we've just been talking about rotational motion and things like that. I showed you guys some gyroscopes. So that's a pretty rich phenomenology when you actually get into the vector nature of angular momentum. So I showed you that, and I'd encourage you to, play around with wheels, bicycle wheels, spinning objects in general, do a lot of interesting things. But we're going to go back to the fixed, what we call the fixed axis motion, which is easier to deal with, and for which we have an entire theory built up at this point. So I want to get to that, but before that, I'm going to review a bit, because we had a quiz recently. So I'm just going to start off with the quiz number 7 question and work that, and then I'll look at a couple of homework problems, and we'll put all the rotational motion formulas back up on the board. So quiz number 7, we had that. This was actually a homework problem, I'm pretty sure. We had MV, so we've got a bullet, and it's going to hit this pendulum bob and go right through. But when it comes out, it has half the speed. But because there's conservation of angular momentum, this thing gets whipped all the way around up to here. And it's not a string that's supporting it, it's a rigid massless rod that's supporting the pendulum bob there. So this thing was capital M, and we had momentum, and we would say mv before the collision is equal to mv prime after the collision. They're not stuck together, right? It's passing through, but this thing picked up some motion, and then we had a half mv, which is what the bullet had on its way out. So that allows us to solve for v prime, and we're going to have mv minus a half mv, so we'll have mv over 2 on this side divided by capital M. So we'll have mv divided by 2 capital M. So we'll hold on to this result. But then for the pendulum bob, we have energy. And it starts out, say, just with kinetic energy, so 1/2 mv prime squared. And it just barely makes it to the top here. This was L, so that's a height 2L, so that is equal to mg, and instead of h, well, we could write h, but that is 2 times L. Okay, and so this simplifies as well. V prime squared is equal to, you get a 2 and a 2 is a 4 times g times L. So we'll hold on to that as well, and then we can solve the whole thing. So we've got our v prime, so we have mv over 2 capital M squared is equal to 4gl, and we're just going to solve for the v. So the v, we're going to have 2 squared is 4, we're going to have 16 gl, v squared for starters, okay, 16 gl, and then we'll have m squared over m squared. And when you simplify that, you have 4m divided by m root g times L. And that was where you could plug in your 2 m's and your L and get the final answer, V, on quiz number 7. Good, so we had that. Now there was a homework problem. It's an older homework problem. I think it's been turned in by now. Let me try to find, was that unwinding spool problem? So that was 90. Pretty sure I assigned that. I was going to. So let's, yeah. Problem 90, part A. So this is an interesting 890. So we have a disk here, M, radius R, and I can use another color. It's wrapped with the string, and it's suspended here, and it's unwinding. So we have two forms of Newton's law. We have, I'll go ahead and write that here. We have F equals MA, so the net force, and we have the net torque equals I alpha, and we have alpha R is equal to A, relating the angular acceleration and linear acceleration. So let's see, let's go ahead and number these. Now, what about the net force? Here we have a tension, and here we have a weight. Okay. So for the first equation, we would say tension. In fact, I'm going to go ahead and make this the positive direction. So we'll have mg minus t is equal to ma. Right, we're going down in the positive direction. So mg pulling down minus t, and this is supposed to be an uppercase m, so let's go ahead and work with that. So that's one equation. And as far as the net torque goes, you'll notice this force, there are only these two forces acting here. This force, the weight, does not produce a torque around the center axis here. So we will use that torque. So for torque equals I alpha, we're going to have T times R is equal to I alpha. Now, moment of inertia is a half m r squared, and the alpha is the acceleration divided by r. So A divided by r. And what that does is it cancels all the r's, because we have r squared divided by r, that's one power, they cancel on both sides. And what we have now is a second equation for the tension. T is equal to 1/2 ma. So there's our second equation. And now we can go ahead and plug these in. So we have mg minus 1/2 ma is equal to m times a, so that mg is equal to ma plus 1/2 ma, which is 3/2 ma, and therefore we get a is equal to 2/3 g. Pretty sure that's what the book said as well. Yes, wonderful. So we're going to leave it at that. Again, one of those things you could never guess. You have to go through with the whole system. And we use two forms of Newton's law. So that is really an interesting problem. Use both of these forms of Newton's law. We made use of this thing as well. Okay. So I want to go back to the full formalism on this equation here, right? The rotational version of Newton's law. And just say a few more things about it, bring a few more things into play. I'll send this up here. Okay, so I'm going to begin by just setting out the full equations without writing all the linear ones down this time. We know there are linear versions of these equations, but we have angle, we have delta theta, we have omega equals delta theta divided by delta t, and we have alpha equals delta omega over delta t. And these were just created just analogously to position, displacement, velocity, acceleration, except they're angular displacement, angular velocity, angular acceleration. So there is a relation between these and the linear expressions, and S is equal to R theta, V is equal to R omega, A is equal to R alpha. So we can use these when we, as we just did up there a moment ago. Okay. So those are our our rotational quantities. Also, we have the whole kinematic equations that I'm not going to write down at the moment. Constant acceleration kinematics. Okay. But then we came to dynamics. And we had that equation up here, Newton's law for rotational motion. But first we have to mention, I'll be a little more explicit now, torque, tau, I'm just going to write FR, force times lever arm, right, twisting force. We have moment of inertia. Well, let's go ahead and write down net torque equals I alpha. So that's our Newton's law of rotation that we just used, with I is equal to the sum over m sub I L sub I squared. And this L sub I is the distance from that mass from the axis of rotation. Then we also had capital L is equal to I omega. That's the one we just learned about last time, the angular momentum. And I can also remind us that we have kinetic energy equals 1/2 I omega squared. So the key to all of these dynamical things is this moment of inertia, which is this mass distribution. So with this formula here, and I'm going to spend a little more time talking about moments of inertia now that we know how important they are. And there's a little table in the book, which I'll reproduce here. Moments of inertia. Okay. So we had the hoop, where all of the mass is the same distance from the center. So hoop of mass m, radius r. There's our hoop. And the moment of inertia is simply mr squared. Okay. All the mass is the same distance from the rotation, from the axis of rotation. Then we had a disk, and that would also be a cylinder. mass m, radius r. So that's solid, uniform disk, and I is equal to 1/2 mr squared. And of course, we remember we learned that this disk is going to roll faster than this hoop, okay, because it has less moment of inertia. So remember that we were talking about the rolling races on that. And then the sphere mass m and radius r. So I'll just draw it like that. 2/5 mr squared. Now, I was looking in the text, they gave us a hollow sphere, interesting as well. Where was this? Yeah, so they had the long, thin rod, and yeah, I had not given you numbers for these. So if you have a uniform rod, ML, and the axis is through the center, okay, so you're rotating it like this, then the moment of inertia is 1/12. I equals 1/12 ml squared. And if you're rotating about an axis that goes through the end here, so that was my demonstration of just grabbing the ruler, rotating like that. And if you've tried these things, and you should try them, you'd recognize how much different that is. That one is 1/3. 1/3 ml squared. Okay, it's always a mass times some length squared. That comes out of its definition. And I'm going to spend a little more time on this one because there's a general theorem where if you know these, you can get many more moments of inertia. And it's not in your book, I don't think, but I'm going to put it up here. Now, all of these moments of inertia are with respect to the center of mass, except for the last one. Okay, this one here, the center of mass is at the center of the ruler. Okay, this last one it's not. So this is actually an example of a theorem called the parallel axis theorem. Go ahead and put that down for us. So this is still the topic of moments of inertia. It's called parallel axis theorem. And what it says is this: suppose you have an object. We're going to do it this way. So here's an object, and there's an axis, and we're going to imagine if we rotate about the axis there, that's the moment of inertia with respect to the center of mass. Now, if I take that same object and rotate it about an axis over here that's parallel, a distance d from this axis here, okay, then the moment of inertia with respect to this axis is equal to the total mass d squared plus the center of mass moment of inertia. This is the parallel axis theorem. That is to say, the moment of inertia of this object here is, say it's spinning around this blue axis. That would be the center of mass moment of inertia. What if I write that a little more separate here? I some center of mass, just to separate those. Okay. But if I swing this entire thing around here, okay, I'm talking about rotating this whole thing around this axis, then the moment of inertia with respect to this axis here is the total mass times d squared, which is what it would be if it were a point mass, plus the moment of inertia of it rotating about its own axis here. So this is a really good theorem because, first of all, what we'll see is this this second expression is just a result of the parallel axis theorem, but you could now rotate spheres, hoops, and other things about an axis that is not the center axis there, center of mass axis, and you could gain all manner of new moments of inertia. Good, so I'm going to prove that statement about the last one. How to check the time, how much time are we going to take for this? Oh, we're good, okay. So the example for the parallel axis theorem is just the relation between these two. Okay. So let's imagine we've got the stick of length L, there's its center of mass, and I, center of mass is equal to 1/12 ml squared. Okay, the stick is total length L. So now if we swing this around this axis here at the end, then we have to have mass times this distance here. What did I call it? D? Well, this distance D is now equal to L over 2. Half the length of that thing. Go ahead and square it. L over 2 squared plus 1/12 ml squared. Now let's see what happens. We've got ml squared, and then we're going to add 1/4, right? Half squared, 1/4 plus 1/12. And that is 16 over 48, which is 1/3. So it checks out. Okay. So it really is 1/3 ml squared. So what other examples could you do with this? Well, suppose here I'm going to do an example with the hoop. Okay. Gotta erase all this stuff. Next example is one whose answer we don't know, but we're using the hoop, and we have, with respect to the center of the hoop, we have I center of mass is equal to m r squared. Okay. Now what if we use an axis? Okay, so by the way, the axis this time is coming straight out of the board. Okay. And this parallel axis is also, so axis into the board, out of the board, okay. So the parallel axis is a distance r away, and with respect to that parallel axis, we have I equal to mr squared. That was that md squared plus mr squared. So that's just 2mr squared. Now, without this, you wouldn't have been able to guess that because the distances of all these points from the axis of rotation are a very complicated function. Okay? But it turns out we just had to add total mass r squared, because that's this term right there, to the original one. So you can do that to any moment of inertia, if you're careful. And now we know the moments of inertia of a much greater class of objects. Okay. So now that we have that, I want to talk a bit about, of course I've erased all the formulas again, but that's okay. I'm going to talk about the rotational quantities again, angular momentum, kinetic energy, and so forth. Okay, so this is just going to be more dynamics. And I'm going to start with, in fact, this may be the exact homework problem, but it's a general situation. Suppose we have a uniform rod, and there's an axle, so an axis that goes right into the board. So, axis into the board here. And of course I got a ruler, I always have a ruler on me, so that's good. And what I'm just going to do is release it and let it swing. Okay. I want to let it swing with no friction. And how fast is it going to be moving as it swings through? So let's do this. Good. Then I'm going to call this A. And then I'm going to have it swing through like I just described. And down here refers to the position B. So the question is, what's the angular speed and what's the linear speed of this thing here? So question, so just to make sure I write this down. So release from rest at A and let swing freely. Okay, so that's what we're doing. We've got the rod, we're releasing it the way I just showed you, letting it swing freely. And then we want to know, find omega at B and find V. Okay, find V, I'll write it out, find velocity of the tip at B, right? Because this thing's swinging through, the further it is from the axis, of course, the faster it's moving. So we want to know the velocity, right, of the very bottom here at B. Okay, so what are we going to do here? This is an energy problem. If I write A and B, there's a chance that it's an energy problem. So the thing started out with no kinetic energy, and we could say it had the potential energy. If this rod is length L, I guess we got to determine that. It started out with the potential energy of the center of mass elevated by L over 2. So we could say we had m g L over 2. That was just the potential energy at A, no kinetic energy yet. And at B, it was 1/2 what? Okay, so potential energy here, down here, it's swinging around. So it has 1/2 I omega squared. Okay. So that's potential energy at A is converted to kinetic energy at B. And now we know that it's 1/2. And the I here is 1/3 ml squared because it's swinging around the end right there. Still up there, yeah, 1/3 ml squared omega squared. So we wanted omega, and we can just say mg L over 2 is equal to ml squared over 6 omega squared, and solve for omega. So that'll be 6 over 2, that'll be 3, omega squared will be 3g divided by L. Okay. When we do that, this is an L. 6 over 2 is 3, that's right. M cancels G over L. So 3G over L. And since we wanted omega, let's go ahead and write this. So omega is equal to root 3G divided by L. Now the question is, what's the speed of the tip? The speed down here at the bottom, V sub tip, or V sub end, or whatever you want to call it, the end of the rod is omega times the length. So that's omega R. And R is L, so omega L. And if we go ahead and take this omega and multiply by L, that'll be L squared under the radical. Cancel one of those L's, that'll be root 3GL. Okay, so why is that interesting? Because if something falls through a distance L, energy conservation will tend to give us root 2GL, and 3 is greater than 2. So the tip is swinging faster than it would be if it were a point mass that had just fallen through that distance. And okay, that has ramifications for other situations as well. Good, let me check the time before we go on. Okay, fantastic. Got nothing but time here. Okay, that was the homework problem I was going to assign. I'll still assign it. Let me see if we have a different one as well. Same example. Or similar example. Similar example. So we let that thing swing through just because easy one to think about. Suppose we take a tower, a uniform tower, for example, a smokestack, and we let it tip over. Okay. So the similar example is that a uniform tower tips over and falls. And the idea is it's going to fall, and that'll be the axis of the, or anywhere there'll be the axis of the point with which it falls. Similar problem. center of mass, okay, is going this way. So this thing is falling. And what we're going to find is that the angular acceleration produces a linear acceleration of the end of this tower that is greater than g. And the only way that's going to happen is if there's some kind of torque along the length of this thing. And what happens in reality is that the tower will actually crack and buckle. So it won't actually fall. It won't fall as a linear object. Eventually it'll crack because of the torques involved. So that's one I should have you guys solve. That'll be a great homework problem. Let me write down the homework problem that I already had, and let's see about this one. Okay, so consulting the back of the chapter. We have homework, and this is what, 29? Homework 29. Chapter 8. So the one I just discussed here is number, one way or the other, is number 47. Okay, this is perfect because I gave you the angular velocity and they're asking for the angular acceleration. Okay, 47. So 47 is this one in terms of the angular accelerations and tangential accelerations, okay? So you're not just going to use the energy method, you're going to use the torque equation. Perfect. And that is the same problem that translates to what's going on here as well. So I'm just going to, I wonder if the book has, if the book doesn't have a picture of towers buckling, I recommend you look for some. I don't think it does. So find an image of a falling smokestack buckling. I've seen them before they exist. They're pretty great. Of smokestack demolition. And what you'll actually see is that as it's falling, it's buckling in the middle like this. Okay. Cracking in the middle. Okay. Pretty good. So chapter 8, problem 47, you'll enjoy that. You gotta get in there with the Newton's laws of rotational motion. You got your moments of inertia, so all the things are at hand. Let's see if we find one more for you guys to do. I already assigned a couple good ones last time. So these are two involved. Okay, number 89 is pretty beautiful too. And as always, formulas first before you plug any numbers in. Don't plug any numbers in until the very end. So yeah, we'll just say 47 and 89, chapter 8. Those are interesting problems. And let me know in the email if you want to see me do these later on next week. Okay, we'll leave it at that and see you guys later.